Hey, Mr. Gusa here with one of our first podcasts about stoichiometry. And specifically, what we're going to address here is what is stoichiometry and the applications for why we would do stoichiometry. This is kind of when we really start applying our science to some real practical problems we can approach. And our application that we're going to investigate today is an airbag, and specifically, how does an airbag deploy? So here I have a high-speed picture of an airbag over here. And basically what we're trying to do is we're trying to produce an exact quantity of nitrogen gas within an instant. If we overfill that bag just a little bit, the bag is too hard, and so now it's kind of like instead of hitting a nice soft pillow, you're now hitting a bag of cement. Or if it's underfilled, then you're going to just go right through it and hit the steering wheel. So you need to have this kind of filled up precisely, and people's lives are in danger. So here, actually, we have a quick video I'm going to cut to that'll talk about how much engineering kind of goes into this.
Secret is to have a bomb in your car, more specifically, in your steering wheel. Airbags are essentially a combination of sensor, ignition system, explosive device, and nylon balloon. The bomb really is a bomb. The blast is achieved by a controlled ignition of high explosives which are packed in the form of pellets, and the force of the blast pushes air into the balloon at incredible speed. Different vehicles demand different airbags, and their design is improving all the time. For each new design, a 3D virtual model is produced, and from this, a prototype is created. The nylon balloon is made by a combination of precision laser cutting and machine stitching. Before the crash test dummies can be exposed to the airbag itself has to be tested. A steel weight is driven into the steering wheel to ensure the bag can repel the force of the average body at over 40 kilometers per hour. Once the test is completed, any faults are modified by design technicians. Lives depend on the design of these airbags, so every aspect is examined again and again and again. The problem they found here is that the airbag doesn't deflate quickly enough. In a crash, such a simple design fault could cause a driver's neck to snap like a dried-out breadstick. So a solution is found.
Okay, my proposal is that we increase the size of the ventilation holes by, I think, like 30%. Okay. What do you think about that?
Yeah, sounds good.
After modifications have been made, it's back to the stitching room to create the new design. Once this is complete, it's time for the final test to take place.
The person is from maybe a side airbag that's going to deploy, or there's going to be like a different height, so the size of the airbag or the design of the airbag's going to be different. So all the time we're updating kind of different designs on those bags. So there's a lot of engineers who are working on that all the time. And again, we're producing an exact quantity. We can't be off by even just a little bit, because we can really damage somebody. And yet, you know what? You're not going to make a mistake and really hurt someone, because we're going to test it and test it and test it. But what we really need to do is do some science and calculate how much nitrogen gas we're going to produce. And here I have a reaction. This is what's actually happening inside of your airbag. They were talking about there's an explosive inside your airbag. It's this thing called sodium azide right here, NaN3. So there's these pellets of sodium azide within your steering column. It's basically a bomb. When it explodes, pieces of that kind of don't go flying out. There's a little filter to keep that, but the gas that's produced is nitrogen gas. And so that does fill up the bag. It happens very quickly. The bag's very hot. If you've ever been in a car accident where the airbags are deployed, you know that it's not a nice little fluffy pillow that you're landing in. It does save your life, but it's not the most friendly thing to bump into. So here I'm going to put you in a little situation. Say that you are working for a car company, and you design some of these new airbags. And so here I have our reaction for the airbag again. But what we're going to do is we're going to assume that you need 2.75 moles of nitrogen gas to inflate an airbag. So someone's already told you that's how much you need. Your job is to figure out how much of the NaN3 or the sodium azide is needed. So again, the important parts of our problem here are that there's 2.75 moles of N2, and we're asking you how many moles of sodium azide are going to have to be included there. So we're looking up at our problem. This is pretty tough. Before we were doing mole calculations, but we were just changing back and forth between grams and particles and moles. Now we're being asked to go from moles of one substance to moles of another substance. If I have this much of this, how much of this do I need? And for this, what we're going to use the coefficients from our balanced equation. So if I wanted to find out what my ratio is of NaN3, the sodium azide, to our nitrogen gas, then what I'm going to do is I'm going to use the coefficients out in front, which happen to be the 2 and the 3 right here. That's going to be my ratio. So if I had 2 molecules of NaN3, and I had 3, that would produce for me 3 molecules of N2. Now, the molecules are on a scale so small that we'll never be able to deal with it. Like, you can't measure out 2 molecules of NaN3. It just doesn't happen. It's so infinitely small. So what we do is we work these things up to a mole size. So if I have 2 moles of NaN3, that's 2 times 6.02 times 10 to the 23rd molecules of sodium azide. That will produce for me, after it breaks down, 3 moles of nitrogen gas. That is 3 times 6.2 times 10 to the 23rd molecules of the nitrogen gas. So what I'm really doing here is I'm doing a ratio. So for that ratio here, if I wanted to actually calculate my answer here, going back to our original problem with our 2.75 moles of N2 gas, what I'm going to do is I'm going to set up my dimensional analysis chart, just like we had done before. I'm going to start with 2.75 moles of sodium azide, of nitrogen here. That's what our starting value is. Now what I'm going to put into there is our ratio right here, except for I have moles and moles, so which one do I put on the bottom? Now this this unit that I have here next to moles is really important. I know that what's going to go down, because I have to cancel out my units, is going to be moles of N2 on the bottom, and then because that's what's on the bottom, I'm going to put moles of NaN3, the sodium azide, on the top of my chart here. Finish my chart. And so now the coefficients that are going to come down, well, my coefficient for NaN3 is a 2, and my coefficient for N2 is a 3. So this is the correct way to put those numbers. So before, when we were doing mole calculations, which unit I have, like the compound itself, wasn't necessarily that important. Now it is, because I otherwise have moles over moles, and you're going to get confused and accidentally flip them one upside down on the other. And so when you go to do this calculation now, you're going to multiply straight across. You're going to multiply 2.75 times 2, and then you're going to divide that whole thing by what's in the denominator, the 3. So 2.75 times 2 divided by 3 is going to be equal to 1.83 moles of sodium azide. So if you were at work and they asked you to design this new airbag, you'd know exactly how much to put in there. But so what is stoich? What is this whole idea of stoichiometry, what we're doing? Stoichiometry is the process of determining how much product is made or how much reactant is needed during a chemical reaction. This is when we can finally start asking you guys in a chemical reaction this question of how much is either going to be made or how much is going to be needed. This is very similar to something like a recipe. Well, if I'm going to be making this many chocolate chip cookies, how much of the baking soda am I going to use inside my recipe, and so forth. Alright, so going back to our equation again here, what we're really looking at, the really important part of stoichiometry is this ratio from our balanced equation, these coefficients that we have here. And so what stoichiometry enables us to do is we can use the mole relationships. So if I had to come up with a mole relationship for this problem here, it'd be a 2 to 2 to 3 ratio of sodium azide to sodium to nitrogen. So what we can do is we can start making predictions about, well, if I need to produce a certain quantity of N2, how much, how much sodium azide do we need? Or if, say, I give you a certain quantity of sodium azide, we can ask you how much of my product can be produced. And the other nice part about stoichiometry, as soon as we get to this, now we can start actually getting into the lab and actually doing some experiments where we can be a lot more quantitative, meaning using numbers and measurements in those labs. So far during first semester, we've done a lot of qualitative labs. So we're looking for what's the change, or what colors produced, or kind of labs that are more qualitative, or they don't have numeric calculations associated with them, but more qualitative or observations made. So now we're going to get a lot more into quantitative chemistry. So thinking through our thought diagram for stoichiometry, the whole key behind this is we can go from moles of some substance, we'll call the substance A, to moles of substance B. And the way that we go back and forth between, say, moles A and moles B is going to be the coefficients in a balanced equation. So what you're going to need is you're going to need a balanced equation with some coefficients. So I would need a 2 right there. So that'd be a 1 and a 1. So what we're going to use for our going back and forth between moles and moles, we're going to use a ratio of the moles. An example of that mole ratio would be here in my problem. It would be 2 moles of B to 1 mole of A from our equation that I have there. Alright, so I can use that to go back and forth between moles. Now this doesn't mean that I can't still do the same steps that I've done before. For example, once I've calculated how many moles of B I need, I can still calculate how many grams of B I need. And so to go back and forth between moles and grams, just like we did last unit, we're going to use our equality that 1 mole of a substance is equal to, or in this case it's B, is equal to the molar mass of B in grams. And so I can use that to go back and forth. I can also take B and I can turn it into how many either atoms or molecules or formula units we have. And so the way that I go back and forth between those things is I use another quality, that 1 mole of B, or any substance, is going to be equal to 6.02 times 10 to the 23rd particles of that substance. Alright, on the other end, if I want to, before I do a mole ratio calculation, I could do the same thing, going back and forth between grams of A and particles of A. this case, again, 1 mole of A is going to equal the molar mass of A in grams, and 1 mole of A is equal to 6.02 times 10 to the 23rd particles of A. So this is going to rely a lot on our mole unit, kind of right before we ended first semester when we talked about moles. This whole process right here is basically our mole calculations. We've already done that. This whole part over here, that's also mole calculations. You've already done all that. All you have to do is this one goofy step in the middle where you go from moles of some substance and you change it into moles of another substance. And the way you use that again is your mole ratio here. So that's kind of the key part of stoichiometry. So let's look at some example problems. So the first one here, how many moles of potassium chlorate, KClO3, must decompose in order to produce 9 moles of oxygen gas? Now, the key part of stoichiometry is going to be this mole to mole ratio. In this case, we're trying to find the ratio between KClO3, the potassium chlorate, and oxygen. Except for where do we get that from? We get that from a balanced equation, which we don't have a balanced equation for that right now. So if we look at our question, it tells us that it's a decomposition reaction. So if you remember our form for a decomposition reaction, that's going to be AB breaks down into A plus B. So what we know about our equation here is that we start off with KClO3 because it says that's what's decomposing. And it tells us that one of the products is going to be oxygen gas. What's going to be left is KCl. And potassium is has a positive charge, chlorine has a negative 1 charge, so those cancel out. We have to balance our equation. So when I go to balance our equation, we're going to get 2, 3, 2. Alright, so now let's look at our question prompt. It's asking us for how many moles of KClO3. So what it's asking me for is moles KClO3 must decompose in order to produce 9 moles of oxygen gas. So our oxygen, we're going to identify that part. That's over here, 9 moles. And our relationship that we were talking about before, KClO3 is 2 to 3 molecules of oxygen, or moles of oxygen. So we're going to set up our chart, and we start off in there with our starting value, 9 moles of oxygen. So now actually adding that oxygen is very important to our mole calculation, because this part of our chart, this unit, we know has to cancel out. So we're going to move it down in our chart so it ends up in the denominator, moles of O2. And I can turn moles of O2 into moles KClO3 using our ratio that we just made up here. So next to O2 is going to go a 3. Next to KClO3 is going to go a 2. So we had to make sure that our units of moles and oxygen cancel out. So we go through, we enter these values into our calculator. This is going to be 9 times 2 is 18, divided by 3 is 6 moles of potassium chlorate. So we still set up our dimensional analysis chart. We still cancel out all of our units in the same way, so we don't have to try to memorize anything. But the key part is we have to use a balanced chemical equation. You can't get away from having a balanced chemical equation. All right, let's try to make this one little step harder. Say that we have the same problem, Except for now, instead of asking you for moles of KClO3, now we have grams of KClO3. Now it's going to be a little bit different. So here we have 2 KClO3, or it forms 2 KCl and 3 O2. This is the same reaction as before. And so if I'm going to label in our reaction kind of what they're asking us for, now it's asking us how many grams of KClO3, and it tells me that we have, again, 9 moles of oxygen. So when I go to start this off again, I need to look for what's my ratio of KClO3 to oxygen. And so we look at our coefficients in our balanced equation. We're going to have 2, and we're going to have 3. So that's my ratio. So I'm going to make our dimensional analysis chart. I'm going to start with 9 moles of oxygen. Just like last time, I know that I have to cancel this unit out, moles oxygen. So I'm going to cancel it out by putting it in the denominator. And I can turn it into moles of the potassium chlorate using the ratios that we came up with from our balanced equation. Make sure you put those in the right place. And these units cancel out, so moles of oxygen cancels out. So if I stop right now, I'd end up with moles of KClO3. Now if you think back to our last unit when we were doing moles, if I just gave you a problem from there and said we have this many moles of KClO3, how many grams is that? You would tell me, well, the equality that we know for that is 1 mole of KClO3 is equal to the molar mass of KClO3 in grams. So the next thing we need to do is we need to reference our periodic table to look up the molar mass of KClO3. So you look that up. I'll give you guys a couple seconds to start looking those things up. Potassium 39.1, chlorine 35.45, oxygen 16. You add those all together, you should get 122.55. So 1 mole of potassium chlorate is 122.55 grams. Well, so right now, right in my chart, I can add another step. Just like before, I need to make sure that I cancel my units out. So my moles, KClO3, are going to go in the denominator. And what I'm going to try and turn that into using a mole conversion is grams KClO3. So now I'm going to go back and I'm going to reference my relationship up here. I know that 1 mole of KClO3 is equal to 122.55 grams potassium chlorate. And when I look back, moles potassium chlorate now cancels out. And if you calculate everything across in my chart here, 9 times 2 times 122.55 divided by 3 should equal 735.30 grams of potassium chlorate. So this is really a stoichiometry problem because I have to go from grams or moles of one substance to moles of another substance. This part right here, that's stoic. The other section that's over here, this is just a unit conversion. The fact of the matter is, from our last problem, the 6 moles of potassium chlorate that we calculated that really is the same thing as 735 grams. So from our last problem, the 6 moles is equal to 735 grams. It's just a difference in the unit, but they represent the same quantity of material. Let's talk about one last problem here. This one's a little bit different. So here we have, it asks us how many grams of silver will be formed from 12 grams of copper, and I'll give you a reaction to use it with. So this is a quick calculation for us, but what we're being asked for this time is we're giving you how many grams of copper we have, and it's asking how many grams of silver. Well, silver over here is Ag. If you don't remember how to remember that, Au hands off my gold. Well, Ag is the other one. So Ag, that's what it's asking us for in grams. And if we look at what our relationship is for our copper to silver relationship, is going to be a 1 to 2 relationship in terms of the coefficients from our balanced equation. The problem is that I can't really do that problem yet because here I have moles of copper, and then I can cancel out moles of copper and get to moles of silver. And this is where I use my 2 to 1 relationship there. And the problem is I don't know how many moles of copper I have. But what I can do is I can find out how many moles of copper. You guys know how to do that. Because over here, I know that I have 12 grams of copper. And I know that our relationship, again, is 1 mole of any substance is equal to its molar mass in grams. So if I want to get rid of grams of copper and turn it into moles of copper, I'm going to use my molar mass. I'm going to use my equality here. 1 mole of copper is equal to the molar mass, so you look it up on the periodic table. And that number is 63.55 grams. So 1 mole of copper is 63.55 grams of copper. And so now, successfully, I can use, remember, this step right here is stoichiometry. I have to do this calculation before it over here just to get in the right unit. So this is just a unit conversion. You can't have some relationship here for unit conversions. It just doesn't work. You need to be talking about moles. Now the other thing, the problem asks us to end in grams of silver. So I'm going to add another bracket onto our problem. And I know that I want to cancel out moles of silver. And I can cancel out moles of silver with grams of silver using my same relationship as before. That 1 mole of any substance is equal to its molar mass. If you look silver up on the periodic table, that's 107.87 grams of silver. And so let's go through and make sure that all of our units cancel out. We start off with grams of copper, and that cancels out with grams of copper. After that, we went to moles of copper, and we cancel out moles of copper with moles of copper. After that, we ended up at moles of silver. And I want to cancel out moles of silver and end up with grams of silver. So in your calculator, you're going to multiply everything in the top by each other. So that's going to be 12 times 1 times 2 times 107.87. And then you're going to divide that by everything in the denominator, which happens to be 63.55, 1, and 1. And the correct value that you should get out of that is 40.74 grams of silver. So in stoichiometry, stoichiometry is really just one step of our chart. It's going from moles of one substance to moles of another substance. In this case, it happened to be going from moles of copper, or grams of copper in our situation, to moles of silver. Now, you might have to do a unit conversion to put your answer into moles, but really the only difference between this and a mole calculation that you were doing in the previous unit is going to be this center step right here. And it's really not hard. You just have to put in your molar ratio from your balanced equation that we found over here. And then make sure that you cancel out all of your units. And if you're meticulous about writing those units in, now you also have to be meticulous about writing in the compound or the chemical that we're talking about, as opposed to just writing grams or just writing moles. You're going to be just fine. If you're not following this thought process and you're not writing your work out, now's when you might start having some trouble. Alright, so after this video, you should be able to now start working on, in class, your first assignment, the basic stoichiometry.